Hello, good morning everyone. In this class, we are going to study the effect of magnetic effect of a current flowing through a straight carrying conductor. So come, let us start. In this session, I have taken a lot of problems. They may be simple, they may be difficult. Some are from JEE Advanced, some are from JEE Main. So please be patient, have patience, and just go through every numerical. Everything is simple and it is based on formula. So come, let us start. See, if a current I flows through a straight wire and we look at point P for the magnetic field, then it is a concentric ring. How can we show that? Again, I will repeat this statement. Current I is flowing through this straight wire and we want to look magnetic field at point P. Then how will we get the direction of magnetic field? It is through an experiment, and that experiment is if we sprinkle or spread some magnetite or iron filings around it, then all the magnetite will align along this. They will make concentric rings. So we will say that the magnetic field lines due to a straight wire are concentric rings. If you want to calculate, if you want to show direction of magnetic field at this point P, then magnetic field lines are like this. If you want to calculate or show the magnetic field at point P, it will be like this. It is a concentric ring. So what is the idea is that whenever you look for the magnetic field at point P, which is in the vicinity of this wire, then it must be on a concentric ring. Magnetic field lines are closed lines and they are a concentric ring in this case. You can just remember in the electrostat, when all these charges were at rest, then if you try to find the direction of electric field at this point P, which was in the vicinity of this wire, it was in this direction, away from the wire, right? And at this point P, it is going into the paper, and at this point A, it is coming out of the paper. So you will say that whenever charge current I is flowing through a wire, then at point P, magnetic field is into the paper, and at point A, it is coming out of the paper. What does it mean? It means that there is a magnetic field line, and at point P it is going inside, and at point A it is coming out. It is the idea. You may just be curious, why is it so? When these charges are at rest, the electric field is in this direction, which is away from the this wire, and in case of all these charges are running, means current is flowing into the wire, then the magnetic field at this point is not in this direction, it is in this direction. Idea behind that is because monopoles don't exist in magnetic field. Here you can get positive charge and negative charge, but in case of magnetic field you can't get monopoles. You can't get north pole and south pole separately, but you can have positive charge and negative charge separately. That is the reason behind it. The direction of electric field and magnetic field, it is a very interesting idea in this case. So it is very important to know the direction of magnetic field due to a straight current carrying conductor. Now let us come to another point. Now we have to learn this formula. Magnetic field due to a straight carrying conductor, it is finite length. It is a finite conductor having current I, and you have to find magnetic field at point P, which is in the vicinity of this current carrying wire. So formula is B is equal to mu naught by 4 pi I by D into sine alpha plus sine beta. This formula is very, very important, and very important to understand what is meaning of D, what is meaning of alpha, and what is meaning of beta. So let us learn what is D and what is alpha and beta. See, this is a straight wire. You have to find magnetic field at point P. So first of all, you drop a perpendicular from that point to straight conductor. Step 1, draw perpendicular from point P on conductor, right? And length of that perpendicular is D. Length of this perpendicular is D, right? So step 1 is draw perpendicular from point P on conductor, and step 2 is what are alpha and beta? Alpha and beta are the angles made by end points of the conductor with the perpendicular. Alpha and beta are the angles made by end points with perpendicular. So it is very important to understand the meaning of D and alpha and beta. Whenever we have to calculate a magnetic field due to a straight wire at a point P, then definitely we should draw perpendicular from that point P on that finite conductor. It is step 1, and step 2 is to get alpha and beta. Alpha and beta are the angles made by perpendicular with the endpoints. Means you have to do 3 things. First, you draw perpendicular from P on the conductor, and step 2, you join endpoints with P. Endpoints with P, right? So you will get alpha and beta, right? This is the idea, total idea. Rest is practice. This is the only thing I will tell today. This is only thing I will teach today, and the rest is practice. This is the only idea. I will repeat again. Whenever you have to calculate magnetic field at point P very close to the current carrying wire which is straight, then you have to do 2 things. Number 1, you draw perpendicular from that point P to the conductor, right? And number 2, you join point P with the endpoints, and you get D and alpha and beta. What is D? D is length of that perpendicular, and alpha and beta are the angles made by the endpoints with the point P. Now this is the very important formula, and this length of this conductor may vary. It may be finite, it may be semi-infinite, it may be infinite. But in all cases, what we have to observe, what we have to do is, first of all, we should draw perpendicular from the point P at which we want to know the magnetic field on the conductor, right? And then join point P with endpoints. So we will write D is length of perpendicular, and perpendicular from P on conductor, right? And alpha and beta are the angle made by endpoints with perpendicular. I will suggest you to stop the video and just make notes. Without making notes, if you are watching videos without making notes, it is useless. It will be in vain, right? So you must make the notes also. Yes. Now we come to another very special case, and it is very, very important. It has been asked in IIT-JEE advanced many times. So this is a finite conductor. It goes from A to B, where AB is having current I is flowing through it, and you want to calculate magnetic field at point P. So what is the idea? What you can see here, that this conductor starts from A and goes to B. How can you draw the perpendicular? So you will say that it will be like this. I think it will be like this. Yes, it will be like this. So whenever you want to draw perpendicular from P to line AB, then you must extrapolate it. You just extrapolate it, then you draw the perpendicular D. In this case, what about the angles made by the endpoints? This point B is making angle alpha, which will be taken as positive. This point A will make angle beta, which will be taken as negative. See, just see the difference. This was point P in this case. These two ends were on the opposite sides of the perpendicular. Then alpha and beta both were taken positive. But in this case, when both points are on the same side of the perpendicular, A and B are on the same sides of the perpendicular, then you will take alpha as positive and beta as negative, right? So B is mu naught by 4 pi I by D sin alpha. Alpha is taken as positive and beta is taken as negative, right? So this will be formula for this case. Now, semi-infinite current carrying conductor. Semi-infinite means it is very long wire, and we want to calculate magnetic field very close to this end. Then in this case, as you can observe that at point P, this angle alpha goes to 90, right? And this beta, which was here, it is making 0. So alpha is 90, beta is 0. So the formula will be same, mu naught by 4 pi I by R sin alpha plus sin beta. Alpha will be 90 degree and beta will be 0 degree. So you will write sin 90 is 1, sin 0 is 0. So your magnetic field will be mu naught by 4 pi I by R. Infinitely long current carrying wire. What does it mean by infinite in this case? Means you are very close to this wire. Infinitely long current carrying wire, it does not mean this wire is very long, some kilometers, right? No. It means that we are looking at for magnetic field at point P, which is very close, which is in vicinity of this wire. So you will say it will be infinite wire. So we should write formula first, mu naught by 4 pi I by D sin alpha plus sin beta. As you can see, alpha is 90 degree in this case, alpha is 90 degree in this case, and beta is also 90 degrees in case. So alpha is 90 degree, beta is 90 degree, sin 90 plus sin 90 is 1 plus 1, that is 2. So this will be mu naught I by 2 pi R, right? Consider this question. This is a wire, current flowing through this is 10 ampere, and this point P, at this point P you are looking for magnetic field, and length of perpendicular from P to conductor is 5 centimeter, and angle made by perpendicular to the end points of the conductor are 60 degree and 30 degree. So you will write the formula mu naught by 4 pi I by D sin alpha plus sin beta. As you know, D is here 5 centimeter, means 5 into 10 to the power minus 2 meter. Alpha is here 60 degree and beta is here 30 degree. So you will write that, and mu naught by 4 pi is 10 to the power minus 7. So 10 to the power minus 7 into sin alpha is sin 60 is root 3 by 2 plus sin 30 is 1 by 2 divided by 5 into 10 to the power minus 2. This will be answer. This must Tesla. This is the magnetic field at point P. Now let us discuss the shape of equilateral triangle. This is an equilateral triangle of length L, side length L, right? Obviously, height of this triangle is L sin 60 using trigonometry. L sin 60, that is L root 3 by 2. As you know, the height of, the distance of centroid from a side is h by 3. So when you will take 1/3 of this, it comes L by 2 root 3. So as a result, you can just learn that distance of centroid from one side is L by 2 root 3, and distance of that centroid from the vertex is double of this, that is L by root 3. So distance of centroid from its base is L by 2 root 3. What is the application of this idea in magnetism? This is equilateral triangle loop of current. Find magnetic field intensity at O. You have to find the intensity of magnetic field at this point A. First of all, let us check the direction of magnetic field at this point O. See, you just take your right hand fingers, right, and you keep your fingers along the current, sense of current, and your palm is towards that point at which you want to know the magnetic field. So this is the idea. I is along this, palm is towards O, and your thumb is coming out. So due to this wire, magnetic field at point O is out of the paper. You see, I R. At this point, for this you say current is going like this, and you have to find magnetic field at O, your thumb coming outside. So magnetic field due to this wire at O is again out of the paper. Now you come at this point. See, current is coming like this. You keep your fingers along the sense of current and your palm towards point O at which you want to know the electric field. So current here, palm here, thumb goes outside. So magnetic field due to this part of length is again out of the paper. So magnetic field at point O is not zero. All the magnetic field will be add up. So all are coming outside. So it is very simple. Keep your right hand fingers along the sense of current of the conductor. Your palm is towards that point at which you want to find electric magnetic field, and thumb goes up. Due to this wire, field is outside. This wire, field is outside. This wire, field is outside. That is, all fields will add up and it will not cancelled out. So we will say that B net is 3 times of the magnetic field. First of all, we calculate magnetic field due to one wire on this O, and this is the formula for that, and we just multiply by 3, right? What is D here? D is the length of perpendicular from the point O to here. If this is A, this will be A by 2 root 3. So you will write here D is A by 2 root 3. And what are alpha and beta? Alpha and beta are the angle between perpendicular and the end points. This is 60 degree, this was 30, so this is 60 degree, again this is 60 degree. So you will write sine 60 plus sine 60. That is this. That is the net magnetic field at point O. So first of all, very important to learn the distance of geometrical center with the base is L by 2 root 3, and then you should know the direction of magnetic field, that due to all these wires, magnetic field direction of magnetic field at point O is outwards. And that is the idea when you have to keep your fingers along the sense of current, and your palm should be towards that point at which you have to find magnetic field, and your extended thumb will give the direction of magnetic field. So all fields will add up, and that is the formula for the one wire, and then you multiply by 3. You keep D, length of perpendicular, as A by 2 root 3, and alpha and beta 60 and 60 degree. You will get this magnetic field. This is the magnetic field at the center of the current carrying wire, current carrying loop, which is equilateral in shape. You must calculate this and do by yourself. Okay. Now we should come to next another planar figure, that is square loop of current having current I, and length of this square is I A, and you have to find magnetic field at point O. First of all, you should learn the direction of magnetic field. See, keep your fingers along the sense of current, right? Keep your palm towards the O. It comes out again for this, out, again for this, out, again for this, out. So all the 4 sides will have magnetic field in the direction of upwards due to at point O. So what is the idea? That we should calculate magnetic field due to one wire, and just multiply it by 4, and magnetic field due to one wire, one straight wire on O. Formula for that is this much I have written earlier. So what is D here? D is length of perpendicular. If this is A, then this is A by 2. So you will write D as A by 2. And what are alpha and beta? Alpha and beta are angle made by perpendicular with the ends. that is 45 degree and 45 degree, right? This is 45 and this is 45. So this is 45 degree and this is 45 degree, right? So when you will solve this, you must get the result. Please just solve, do not write it directly, right? So we have seen the magnetic field due to a equilateral triangle and due to a square at its center. Now let us come to next planar figure, rectangular loop of current. You have to find magnetic field at point O, right? This has 4 parts, 1, 2, 3, 4. All parts have same effect on O. B is coming out of the plane. So we have to find magnetic field at O. Let us see what we will do. See, just we name these conductors 1 and 2 and 3 and 4. As you can see, this 1 and 3 are identical for O and 2 and 4 are identical for O. So we will say B net is 2 times B1 plus B2, because all magnetic field is adding up. It is coming out of the plane. So 2 times B1 plus B2, right? Now B1 is due to this wire on the center and B2 is due to this wire on the center. As you can see, this length is, total length is a root 3. This length will be a root 3 by 2 and this is a by 2. So you can get sine alpha. Sine alpha is perpendicular by hypotenuse, that is this by this, right? Sine alpha is opposite by hypotenuse, that is root 3 by 2. So alpha is 60 degree. And you can calculate B1. So B1 is due to this wire on the O, is formula will be this, the same formula. What will be D here? D will be this much, a by 2, right? And angle alpha is 60 degree and 60 degree. So you will write sine 60 and sine 60. Now we come at this wire. What is the magnetic field due to this wire on O? We will write the formula again, right? What is the value of D? Length of perpendicular point O from on this, and this is total is a root 3. So this length will be a root 3 by 2. So you will write D here, a root 3 by 2. And what is the angle made by the end points here and here? If this is 60 degree, this will be 30 degree and this will be the 30 degree. So sine 30 plus sine 30. So when you will add these two magnetic fields and make it double, then you will get this answer. My suggestion is that you must do this problem by yourself. So pause the video and just do it by yourself, right? It is very interesting question that you have 4 parts, 1, 2, 3 and 4. 1 and 3 are symmetrical about O, 2 and 4 are symmetrical about O, and all the fields are adding up at O. So B net will be equal to 2 times B1 plus B2. So what you have to do is calculate due to 1 this wire on this, that is draw perpendicular on this, get the length of this perpendicular, get this angle and this angle, you will get B1. Now due to B2 you draw perpendicular on this, you get this angle and this angle, and then you get B2, right? Now you add these two and you will get this answer. So we have studied the magnetic field due to, till now what we have done, we have calculated magnetic field due to a equilateral triangle loop at its center, and due to square loop at its center, and due to a rectangular loop at center. Now can you guess what is the next figure? Next figure is the hexagonal loop of current. There is a hexagonal loop having current I and side A. You have to find magnetic field at point O. So obviously all these currents, all these magnetic field which add up. See, keep your fingers along this, your palm is towards O, thumb is coming outside. Due to this, again all the field is adding up. So what is the idea? That you calculate due to 1 hour and just make it 6 times, then your answer is 6 times B1. So you have to calculate the magnetic field due to only one part. This is only one part. So you have to find magnetic field at O. What was the first idea? You should draw perpendicular from O to that finite conductor. Length of this perpendicular, this is an equilateral triangle AAA. So length of this perpendicular is A sine 60, that is A root 3 by 2. And angle made by this perpendicular with end points is 30 degree and 30 degree. So you will write mu naught by 4 pi I by d. At d, in place of d, you will write length of this perpendicular, that is A root 3 by 2, and alpha is 30 degree and 30 degree. So sine alpha and sine beta, both are 30 degree and 30 degree. This is the magnetic field due to one wire, and there are 6 wires like this, and magnetic field will be add up, you will get this answer. Please pause the video, do it by yourself again. Don't copy and don't make notes. Don't make notes. Don't make just notes. You make notes, but you just do it by yourself, please also. Now there is a regular polygon loop of current, n-sided polygon. N-sided polygon. As you know that n-side polygon is here. Current I is flowing through this, and side of that polygon is A. You have to find magnetic field at point O, right? So this is the idea. This angle will be 2 pi by n. This angle is surrounded by n sides. So one side will subtend angle 2 pi by n at point O. So what will the formula for O? The same formula which I have written earlier. Due to one wire into n, mu naught by 4 pi I by d sine alpha plus sine beta into n, right? What will be d? How will you get d here? So you just draw perpendicular from this like this. This angle is pi by n. This angle is pi by n. When you draw perpendicular, this is half of 2 pi by n. This is pi by n. This you want to calculate this d. This length was a by 2. So if you want to calculate d, you will use tan pi by n. Tan theta is this by this. So tan pi by n is equal to a by 2 by d. A by 2 by d. So d is, you can calculate d from here. D is a by 2 cot pi by n. In place of d, you will write a by 2 cot of pi by n. And in place of alpha and beta, you will write it is pi by n. Because alpha and beta are the angle made by end points with the perpendicular, and that is pi by n, and this is pi by n. So this is the result. This is the magnetic field at center O due to a polygon having side A, and you want to find the magnetic field at point O. So we will use the same formula again, mu naught by 4 pi I by d sine alpha plus sine beta, and we will write in place of d, we will write this much, this one, a by 2 cot pi by n. You have to just take just a simple geometry. This is angle pi by n. You will do like this. Now I'll make a little change in this problem, right? In place of, in earlier problem, a was side of this polygon. Now I made a little change. There is another problem. This is a regular polygon, n-sided polygon, whose side is not A. Distance of the center from vertex is A, right? You have to find magnetic field at O. So obviously you will write again the same formula due to the same conductor. It is mu naught by 4 pi I by d sine alpha plus sine beta. What will be d here? So first of all, you should make a triangle here. So this angle is obviously 2 pi by n, because this point is surrounded by n sides. So this angle is pi by n. This is d. This is a. To calculate d, you will use cos. Cos theta is base by hypotenuse. Cos pi by n is d by a. So d is a cos pi by n, right? So d is a cos pi by n. In previous problem, you took value of d as a by 2 cot pi by n, right? In this case, it is a cos pi by n, right? In earlier, it was a by 2 cot pi n, yes. Here, it was a cos pi by n. What was alpha and beta? Both were pi by n. So you will get this result. Now it is very interesting. This is the formula for magnetic field at center of a regular polygon having n sides. Now what will happen when n tends to infinity? N-sided polygon changes into circle. When n tends to infinity, it will convert into a circle. So you will get formula for the circular loop. As you will learn in your limit and continuity chapter, you have a simple formula. Limit of theta tends to 0, sine theta by theta is 1, and limit of theta tends to 0, tan theta by theta is 1. When limit goes from tends to 0, right? So you write pi by n here. Here is pi by n, that is theta. Here is pi by n. So tan theta by theta, n tends to infinity. So pi by n tends to 0. So tan theta by theta, that is 1. So your formula becomes mu naught I by 2a, which is very interesting formula. You can derive it from the regular polygon magnetic field at center. So that is mu naught I by 2a. There is no pi here. There is no pi here. But due to infinite long wire, you get mu naught I by 2 pi a. 2 pi a. Right? 2 pi a. But here is no pi. Now you come, we will discuss some numericals. We will practice some problems. So here is a straight conductor. It is a wire which is bent like this. This wire has 3 parts. First part is here, second part is here, current I is flowing through this, third part is here. You have to find magnetic field at point P, right? So what you will write, that magnetic field at point P will be equal to B1 plus B2 plus B3, right? Okay. See, B2, in earlier lecture I have discussed, when you will extrapolate a straight conductor and all the points which will lie on this conductor will have 0 magnetic field, right? So magnetic field at point P due to 2 will be 0, right? Magnetic field at point P due to part 2 of the conductor is 0. Now consider this part 1. You just keep your fingers along the sense of current, and palm is towards P, ideal cross R, I towards your fingers along the sense of current, palm towards P, your thumb goes inside. So due to part 1, magnetic field is into the paper, and due to part 2, you keep your right hand fingers along the sense of current, right? Along the sense of current, and your palm towards P, your thumb comes out. So B is towards out, and both are symmetrical about point P. So you will say that they will be cancelled out. B1 and B3 will have 0 effect. They will have 0 effect. So answer will be 0. Magnetic field at point P will be 0. So because this is a semi-infinite wire, this is also semi-infinite wire, and this is finite. Due to part 2 of the conductor, magnetic field at point P will be 0. Due to part 1 of the conductor, magnetic field at point P will be into the paper, and due to part 3 of the conductor, magnetic field at point P is out of the paper. 1 and 3 are semiconductors, means they will have same formula, but they are in opposite directions. So magnetic field at point P will be 0. Now let us discuss this problem. This is a straight wire, infinite, very sufficient long wire, which is bent such that first one part is making angle 90 degree with the other part. You have to find magnetic field at point P. So this is coming from infinite, this is going to infinite. So here are 2 parts. So I will say first part to this conductor and second part to this conductor. Current I is flowing through this, right? So what will you say? This part is B net is B1 plus B2, right? What is the direction of magnetic field due to part 1? Keep your right hand fingers along the sense of current, palm towards P, thumb goes inside, that is B1 is inside into the paper, right? What about B2? Keep your right hand fingers along the sense of current and your palm towards P, your thumb goes into the paper, so it is again into the paper. So what will I do? I will calculate first part and make it double because both have same effects. So what about this part 1? I will write formula. I will write the formula. This is mu naught by 4 pi I by d sin alpha plus sin beta. What will be d here? D is length of perpendicular drawn from here, and that was A. And what was alpha? This end was making angle 90 degree with the perpendicular, so alpha will be 90 degree, so sin alpha will be 1. And this end is, this wire has two ends, this end is making angle 90 degree with the perpendicular, so sin 90, and this end is making angle 45 degree with the perpendicular, so this will be 1 by root 2. So this is the magnetic field due to one wire, and this will have the same calculation, so you will make it just double, so you will get the answer this much. You will get the answer mu naught by 4 pi I by A into 1 plus 1 by root 2 into 2. This is the magnetic field at point P. Now let us discuss the magnetic field at point P in this case due to this system. So this conductor has three parts, first, second and third, right? So you will write B net will be equal to B1 plus B2 plus B3. So what will you say? Due to part 2, magnetic field will be 0 because the point at which you have to find it is coming along the line, it is on the line, that's why magnetic field at P will be 0. Now let us see what is direction of magnetic field at P due to this part 1. You should keep your fingers along the sense of current and your palm towards P, your thumb goes inside. So due to part 1, field is inside into the paper, and due to part 3, what happens when this current is going, your fingers are along the sense of current, your palm is towards P, thumb is inside, this is again inside. So what will you do? You just make calculation for 1 hour and one wire and make it double, you will get the answer. So write down the same formula. What will be D here? D is perpendicular of that point. D is perpendicular from point P to this conductor, from point P to this conductor, and this is D. So D is A, this was A, so this was A. And what is alpha and beta? What are alpha and beta? This end of wire is making, this is perpendicular, this end of wire is making angle 90 degree with the perpendicular, so alpha is 90 degree, and this end of wire should be on the another side, but it is on the same side, so it will be taken as negative, so it is minus 45 degree. Already it is given that this angle is 45 degree. Both ends are on the same side. Earlier I have said whenever this end is on, both ends are on the same side, then this will be positive and this will be taken as negative. So this angle, this wire, this end is making angle 45 degree with this perpendicular, and this angle is 45 degree, and it will be negative. If this were from up to this side, then we will take it positive, right? So it is minus 45 degree. So you will write mu naught by 4 pi into I by A into 1 minus 1 by root 2 into 2. This is the whole idea. Now you have to calculate magnetic field at point P. It is very simple. Part 1, part 2, part 3, right? So magnetic field at point P is B1 plus B2 plus B3. right? Okay, B1 you should first calculate direction of magnetic field, right? Then you write whether B1 plus B2 or B3. What is direction of magnetic field at point P due to 1? Keep your right hand fingers in the sense of current. Your palm is towards P, your thumb goes inside. So B1 is into the paper. Due to B2 current, due to part 2 current, magnetic field at P will be 0 because it is on the same conductor. And due to part 3, keep your fingers along the sense of current, keep your palm towards P and your thumb goes out. That is at P magnetic field is out of the paper, that is out of the paper. B net, you will have the same formula, so B net at P will be equal to 0 because B1 and B3 are equal in magnitude but opposite in direction. B1 and B3 are equal in magnitude but opposite in direction at point P, so it will be 0 effect. So now let us come to another problem. It is very interesting. We have 4 wires of same length L. See, there are 4 wires of same length L, and we are making some different figures. From this wire I am making an equilateral triangle. From this wire I am making a square loop. From this wire of length L I am making a this is hexagon, and from this wire I am making a circular loop, right? So then what will you write? This side is A, so L will be 3A, simple. Here you will write L will be 4A, here will be write L equal to 6A, and here will be write L is this length L is perimeter of this circle, that is 2 pi A. From here you will get A is equal to L by 3, from here you will get A equal to L by 4, here you will get A equal to L by 6, here you will get A is equal to L by 2 pi. So as you have calculated earlier that magnetic field at centroid due to triangular equilateral triangle is 9 mu naught I by 2 pi A. You have not to remember this, you must not remember this, you have to calculate in the exam. I have just calculated earlier, just few problems before. It is 9 by 2 pi mu naught I by A, just I have taken from there, right? Otherwise in exam we must calculate, we should not cram it, we should not remember it. So 9 mu naught I by 2 pi A for the equilateral triangle. At the center of this square it will be 2 root 2 mu naught I by pi A. At the center of the hexagon we have earlier calculated root 3 mu naught I by pi A, and at the center of a circle formula is mu naught I by 2A. So here we will write A is equal to L by 3, here we will write L equal to L by 4, here we will write A equal to L by 6, and here we will write A is equal to L by 2 pi, because here A was L by 2 pi, here L by 6, here L by 4, here L by 3, right? Earlier we have calculated this, right? That, see, due to an equilateral triangle it was this much, due to a square it was this much, due to a hexagon it was this much, and due to a circle I have tell it is this much. So I have used these 4 results in this problem. So from a wire of length L, there are 4 wires of length L, we have made 4 different shapes, and we want to calculate ratio of their magnetic fields at the center. So we first of all we just we made an equation in which length of this wire is perimeter of this polygon. We have done it all in all the cases. Here we got L by 3, here we got side was L by 4, here we got side was L by 6, here we got the radius L by 2 pi, right? And now we have just applied the values we got earlier in those problems. Magnetic field at centers were having this formula, and we just kept the value of that side in this case, and we get this ratio. So I will suggest you to calculate all the magnetic fields, and you must calculate this ratio. It has been asked a number of times in your exam. So this was the question, that there are 4 wires having length L, and we have just converted these 4 wires into 4 different shape loops, and we want to calculate the magnitude of we want to calculate the ratio of magnitudes of magnetic field at the center of these polygons, and it was like this. Its answer was this, right? So now come to next problem. Currents I1 and I2 are flowing along x and y axes respectively. Here is x axis, current I1 is flowing through this. Here is y axis, current I2 is flowing through this. Find the locus of point P at which magnetic field is 0. So you have to calculate magnetic field at this point P, right? So suppose this point P has coordinate h comma k. What you do to calculate to find the locus? So distance of this point from here, this value is x, that is h, this value is h, this value is k, right? So magnetic field due to this wire at point P is, I will keep my fingers along the sense of current, my palm towards P and my thumb goes outside. So B1 is outside the paper, and due to this magnetic field at point P, keep your fingers along the sense of current, palm towards P, and B is into the paper. So B2 is into the paper. So magnetic field is possibly 0 in the first quadrant. Let us check, is it possible to have 0 magnetic field in this quadrant? So current is flowing like this, current I is going like this, palm towards P, magnetic field is out of the paper. And what about this? Due to this current, magnetic field at point P is out of the paper. So magnetic field is not 0 in second quadrant, because both fields are adding up, and magnetic field may be 0 in this quadrant, right? What about this? Current is going like this. So magnetic field due to this current wire, you keep your fingers along the sense of current, your palm towards point P, your thumb goes inside. So B is inside. From what due to this? Now keep your fingers along the sense of current, palm towards P, your thumb goes outside. So B is outside, B1, B2 goes outside. So here is possible. So magnetic field is 0 is possible in first quadrant and third quadrant. It is not possible to have 0 in second and fourth quadrant. So if currents I1 and I2 are flowing along the x-axis and y-axis respectively, then it is not possible to have 0 magnetic field in second quadrant and fourth quadrant. It is possible to have 0 magnetic field in first quadrant and fourth quadrant. So B1 will be, what will be formula of B1? B1 will be mu naught I1 by 2 pi r. R is this much. X-axis, for x-axis, this is the distance k. And what will be B2? B2 will be equal to, B2 is this much. Mu naught by 2 pi I2 by r. For this wire, distance of point P is h. Both are equal in magnitude but opposite in direction. So we want magnetic field to be 0. So it will be just cancelled out. Mu naught by 2 pi will be cancelled out. So you will write I1 by, in place of k, you write y is equal to I2 by x. So you will get the formula, you will get the equation, y is equal to how much? I1 by I2 into x. This is the equation of that straight line on which magnetic field will be 0. So what I want to say, that whenever current is flowing along the x-axis, it is I1, and current is flowing along the y-axis, that is I2, then here is a line y is equal to mx, at which magnetic field will be 0 at all points, right? Whether in first quadrant or third quadrant, and slope of that line will be I1 by I2. You just proved it, right? You just made it prove, right? So if current is flowing along x-axis and y-axis, so you are getting the equation of that line at which magnetic field is 0. So it is very interesting problem in SC Verma, that here are 4 wires, right? It is 0 0, intersection of this point is 0 0. Here it is AA, and you want to find magnetic field at point 2 AA, 2A, 2A, right? Here current was I1. In this case current was I2. In this case current was I2. You wanted to find magnetic field at point P. So obviously this system having same current, it is angle 45. All these lines will on the same wire, right? It will make angle 45 degree. You can just see, right? So this is I1 and I2 are equal. So this slope is tan 45, that is 1. So angle is 45 degree. So to this system, magnetic field at point P is 0. And due to this system, here are both again currents are same. So due to this system, magnetic field will be 0. So due to all these 4 wires, magnetic field at point P will be 0. So it was very interesting problem. It has been asked in IIT-JEE main problem also. Now it is very interesting question. Here is a square loop of current. You have to find magnetic field at point O, right? This is a square of side A. Current I is flowing through this loop. You have to find magnetic field at point O, which is distance A by 4 from these 2 wires and 3A by 4 from these 2 wires. So obviously it is not at center. So we should just keep it. You should do like this, that suppose you say this, you say this wire as 1, right, and this wire as 2, right, this wire as 2, this as 3, and this as 4. As you can say, these wires 1 and 4 are equidistant from O. So B1 and B4 will be same value. B1 will be equal to B4. And these 2 wires 2 and 3 are equidistant from this point O. So B2 and B3 will have same values. B1 and B4. This wire and this wire have same magnetic field at O. And this wire will have same magnetic field at O. So B1 will be equal to B4 and B3 will be equal to B2. So what we have to do, we have to calculate magnetic field due to this wire and make it double, and magnetic field due to this wire and make it double, and just add them, you will get the answer. See, now let us come to the next point. So we want to calculate magnetic field due to this part of this wire at point P, right? So what we should do, draw perpendicular from here, from the point P to the conductor, that was A by 4, and this angle A by 4, this angle was 45 degree, and in this case this was 3A by 4 perpendicular. If you want to calculate due to this part of conductor at point P, so this was the perpendicular, its length was 3A by 4, and this was 3A by 4, this is 3A by 4, so this angle is 45 degree. So this angle is 45 degree and this angle is 45 degree. Now we have to calculate these 2 angles, right? So what to do? What about this angle? This is 3A by 4. I have written here. This was A by 4, A by 4. This was 3A by 4, 3A by 4. This angle was alpha, this is alpha. What was the ratio of base and perpendicular? This was A by 4 by this. Ratio was 1:3. So I am just getting interested in ratio of these 2. The ratio of this to this is 1:3. So this will be root 10 by Pythagoras. So you can calculate sin alpha is opposite side by hypotenuse, that is 3 by root 10, right? In this case you want to calculate beta. This was 3 by 4, it is 3 by 4. This was A by 4, it is A by 4. What was their ratio? So their ratio was 3:1, 3:1. This was root 10. So sin beta was opposite side by hypotenuse, that is 1 by root 10, right? So you have calculated sin alpha and sin beta. Now let us come to the question. You want to calculate magnetic field due to this part of wire at the point P. So formula for this is B1 is you have written formula this mu naught by 4 pi I by d sin alpha plus sin beta. This angle was 45 degree. What was d? D was length of perpendicular from P to this point, that was a by 4, and these are the end points which are making angle 45 degree and alpha with the perpendicular. So I have written here sin 45 and sin alpha, and sin alpha you have calculated earlier, it was 3 by root 10. Due to this part it was B2, you have written the formula. D was here 3a by 4, and these 2 points, end points, are making angle beta and 45 degree at point O. So I have written sin 45 degree plus sin beta, and sin beta is, as you have calculated earlier, sin beta is 1 by root 10. So sin beta, you keep sin beta 1 by root 10 here. Now you add these two values, 2b1 plus b2, you will get this answer. So it is very interesting. It is very interesting. It was very easy. It was very easy to calculate magnetic field at center, but when this point O is here, it was difficult to calculate magnetic field at point O, right? So what you have to do, what you have to understand, that 1 and 4 are symmetrical for this point, and 2 and 3 are symmetrical for this point. So we will calculate magnetic field to this part and this part, just add these both and make it double, you will get the answer. So magnetic field due to this part is P1, and in place of D you will write a by 4, and these two end points are making angle 45 degree and alpha, and for this conductor D is 3a by 4, and this part is 45 degree, and this is beta. You have calculated earlier, beta, sin beta is 1 by root 10 and sin alpha is 3 by root 10, right? So when you will add these, because all the magnetic fields are adding up, see, IDL cross R is B, 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 all the fields are adding up. That's why you have added all the magnetic fields. So now the last for this day. So if current divides in a regular shaped polygon, means loop of same material, uniform wire, then magnetic field at center of the polygon due to that loop is 0. See, here is a current carrying loop, here is a current carrying loop, but the current divides, current is not coming in the same direction, it is not loop, it is not loop. Current is coming from here, it is just dividing into two parts, then coming here again, current is just divided in two parts, current is divided in two parts, current is divided in two parts. In all cases, magnetic field due to the loop is 0 at the center of polygon. It has been asked many times in IIT-JEE exam, in NEET also. Whatever be the angle of theta, it is irrelevant of theta, whatever be the theta, magnetic field at center is 0, right? Whatever is theta, magnetic field at center is 0. So it is very interesting that you can prove it also. It is just using Kirchhoff law, because 2 points are in parallel. So I1 current goes this side, I2 current goes this side, resistance of this part, I1 R1 is I2 R2, and when you will calculate it, it becomes 0. Similar is here. Whether theta is 1 degree or 55 degree or 90 degree or 180 degree or anything, 350 degree, whatever theta is, magnetic field at center is 0. What is the criteria? That wire should be uniform. But if wire is not uniform, like here, wire is not uniform, then magnetic field is not 0, right? If wire is not uniform, magnetic field is not 0, right? We will discuss it in next term. So I think it is enough for today, and we will meet again. So please practice these problems for yourself, and just don't make only notes. Making notes is very important to revise and to just summarize things. But please keep your question answers height, solutions height, and solve by yourself, do it by yourself, and go up to the final answer, and then you match. If there is any problem, you can ask me. Thank you so much.